And so the first paper will be welfare maximizing pool testing, presented by Evi Micha.
Thank you very much. So this is a joint work with Simon Finster, Michelle González Amador, Edwin, Francisco Marmolejo, Cossio, and Ariel Procaccia. All of them are in this room, and we are very thrilled for this distinction. So let me start by taking you back in the very recent past, where all of us experienced a lockdown due to COVID-19. And imagine that we are, at the moment, we are a university or an institute wants to return back to in-person activities, but they have the restriction that only people that have been tested negative can return back to their offices. So people that have not been tested at all or have been tested positive should their homes and keep working from there. So when we're thinking about tests for COVID, we usually think of individual tests, where we get a saliva sample from an individual, and then we use an individual test to learn if this person was infected or not. But a technique that was used during the COVID-19 era was the idea of pool testing, where we were getting a number of samples, we pull them all together, and if all of them are negative, then the output of this test is negative, and if at least one is positive, then the output of this test is positive. So this technique is very useful when we want with just one test to catch many people that are negative. So when we have a budget of pool tests, a pool testing regime is how we design which subset of the population is included to each test. So let me go back to the motivating example, where a university or an institute wants to return back to in-person activities, and it has available a limited budget of pool testing. And so the question is, given this limited budget, how we are going to design a pool testing regime. However, because we cannot really test all the individuals of the population, we might want to take into account information like this, that, for example, someone that works in robotics probably really needs access to the robotic labs. Someone that does theory might say that, okay, I'm working on theory, I'm happy staying at my home. Or someone else probably wants to go back to his office with respect to her mental health or other reasons. So in other words, different people probably have different preferences or needs to return back to in-person activities that we want to take into account when we design a pool testing regime. So in this work, we consider exactly this problem, where we have a heterogeneous population, where each individual is characterized by two quantities: her utility to return back to in-person and her probability of being healthy. And so given this heterogeneous population, and given a limited budget of pool testing, the question is how we are going to design a pool testing regime that maximizes the social welfare. So this is the optimization problem that we want to solve. Before I dive into this optimization problem, I would like to mention that this is a problem, a real-life problem, that occurred after discussions that we had with an institute in Mexico. In particular, back to 2021, we had discussions with EC'23, which is a research institute which has around 500 employees. And the situation back then was exactly this. All the employees were under a lockdown. The institute had some pool tests that could use to return people to return back to in-person activities. So I will talk more later about our collaboration with EC'23, but for now, let me focus a bit more on the optimization problem. And let me define things a bit more formally. So given a testing regime, the expected social welfare of this testing regime is calculated as following. First, the probability of a test to be negative is equal to the probability of all the individuals that have been included to be healthy. And here you see that I get the product of the probabilities, which means that we assume independence of the probabilities. And while in general it is probable that there are correlations, because we are under a lockdown scenario, we don't expect people to interact, so we expect these probabilities to be independent. And actually we had conversations with people from EC'23, and they confirmed that indeed they didn't interact this period, and it was safe to make this assumption. Now the expected utility of an individual is equal to her probability to be included in a negative test times her utility. And the expected welfare is the sum of all these individual expected utilities. So this is the quantity that we want to maximize. However, our collaborators in EC'23 had a very particular restriction, which was that they wanted to have testing regimes that are logistically easy to be implemented in practice. And by that, they meant that they wanted to have testing regimes where each individual is included up to one test. And the reason that they had this restriction was that because in practice these testing regimes are implemented by human beings, imagine that someone in a lab, it says, okay, this sample should go to this and this test. This sample should go to this and this test. So by just allowing each sample to be included to 2 or 3 tests, the complication of a testing regime significantly increases. They didn't want that, and so they had the restriction that they wanted testing regimes where each individual is included to one test, which we call them testing regimes without overlaps. However, our first reaction in this restriction was, but what if we lose much by doing that? So our first step was somehow to measure the gain of having overlaps, or what we lose by not having overlaps. And so we measured this as following. Given a particular budget B, we define the gain of having overlaps as the maximum ratio of the optimal expected welfare that we can have when we do allow complicated testing regimes versus the optimal expected welfare that we have when we don't allow overlaps over any instance. So we wanted to see in the worst case for any given value of budget, how large this ratio can be. And our first we observed that even if we have 2 tests available and 3 individuals, the gain of having overlaps is non-negligible. For example, consider this case where we have 3 individuals. All of them have utility equal to 1 to return back to in-person activities. The first 2 individuals have half probability of being negative, and the last individual, let's say that is negative almost with certainty. Then, if we consider all the different testing regimes that we can have without overlaps, if you do the calculations, you can see that the expected welfare that we can have in the best case is 3 over 2. But if we consider this testing regime, where the last individual is included in both tests, then we can see that the expected welfare is equal to 7 over 4, which means that even if we have 2 tests available, the gain of overlapping is equal to 7 over 6, which is not something very negligible. So our question is how bad this ratio can be and how this scales with respect to the value of the budget. Surprisingly for us at least, in this work we saw that for any value of B, for any value of the budget, the gain of overlapping cannot be more than 4. So this ratio cannot really be larger than 4. And I think what is also interesting is that for the case that we have just 2 tests, we were able to show that the gain of overlapping is exactly 7 over 6. So the previous example that I showed you was tied for the case that B equal 2. And in general, this is the only lower bound that we have. So while we saw that in the general case the ratio cannot be larger than 4, the only lower bound is this case when we have 2 tests and it's equal to 7 over 6. We strongly believe that the gain of overlapping is less than 2. We don't have the proof for this, but at least this lower bound that we saw, this upper bound that we showed, convinced us that it is okay to stick to testing regimes without overlaps, which are logistically easy to be implemented in practice. So the next question was how we can find testing regimes, optimal testing regimes without overlaps. But even in this case, we had a barrier because it was already known in the literature that even if we have just 1 test available, it is an NP-hard problem to find the subset that maximizes the expected welfare. So there was no hope to solve this problem exactly. But in the positive side, in the same paper, the author shows a fully polynomial time approximation scheme which worked for B equal to 1. So we had an almost polynomial time algorithm that finds an almost optimal testing regime when we had just 1 test available. So the question is, what can we do when we have more tests available? So in this case, we define the following very simple greedy algorithm. So for the first test, we apply the FP test at the population. We find an almost optimal subset. We include this in the first test, and we disregard these individuals. Then we apply FP test to the remaining individuals in the population. We find an almost optimal subset. We included this in the second test, and so on. We do this until the point that either we run out of tests or we run out of individuals. So this very simple greedy algorithm. And we were able to show that by this greedy algorithm, we have an approximation of almost 5 with respect to the optimal expected welfare that we can have without overlaps. So that was our algorithm, and this is the algorithm that we tested and implemented in EPCIT. So that was the theoretical results, and let me now jump into our collaboration with EPCIT for the remaining of my talk. So let me first give you the whole history for our collaboration. So we started to have discussions with EPC at March 2021. We formalized the problem at September 2021, and by February 2022, we had all the theoretical results, we had the grid algorithm, we have shown that the gain of overlapping was small. So we were ready to run the pilot study and test this grid algorithm in practice. So we immediately started to design the pilot study. However, we needed some ethics approval, so we were waiting until June. And what was really time-consuming was to build an application which was very important for all the communication with the participants of the pilot study, with the testing lab. And in general, we created this application where we included the algorithm there. The testing lab was able to use this app for calculating the optimal testing regime, and then they were loaded back the results of the test. And also, all the communication with the participants was through this application. They were learning the results of the test through this application. We had surveys where we were learning the utilities and the probabilities from this, and I will talk more about this in a while. And if you're curious, you can check this application there. And after having constructed this, we ran the pilot study in September 2022. So now let me focus on the pilot study. So at this point, EPC had already given full access to all the employees. However, they still wanted to test the grid algorithm in practice. So 130 people participated in the pilot study. And we had two goals in this pilot study. First, to test our grid algorithm in practice. And second, to see how the performance and productivity of people is affected when we have a protocol like this, where people cannot just return back to in-person activities without any restriction, but then first they should be included in a negative test. So our first step was to find the utilities and the probabilities of the different individuals. For finding the utilities, we constructed a survey where we had questions in the survey from 3 different categories. So we measured the need of someone to return back to in-person activities with respect to her work, with respect to her mental health, and with respect to her socioeconomic status. And we see the last category as a bonus for a disadvantaged group that had disproportionately affected by a lockdown. And just to give you some examples, from the first category, we had a question related on how much time someone spends in front of the computer during a normal day. From the second category, we had a question related on how happy someone with his life currently. And from the last category, we asked people to indicate in which class they feel that they belong. And these are just some examples. Different answers deserve different points, and they calculated the average value for each individual according to her answer, and that was her utility to return back to her office. For the probabilities, we categorized the individuals into 6 different categories according to their age and to their gender, and then we used a Bayesian model to calculate the probability someone to be infected given that belongs to a particular category. And for doing that, we used publicly available data, census data, and also data from test results in the region that EPC is located. Okay, so we had gathered all the information that we needed. And so we wanted to test our greedy algorithm, how it works, for different values of the budget. To do that, we constructed a mixed integer linear program that was able to find the optimal expected welfare. And we wanted to compare this welfare with what welfare our algorithm was returning. So this is the welfare that the mixed integer linear program was able to find, and this is the welfare of our greedy algorithm. And to do the calculations for you, you can see that the approximation was really, really good in all the cases. And I think what is also interesting is the running time of the 2 different approaches, where you can see that when, for example, we have 35 tests available, the mixed integer linear program needs almost 5 days to find the optimal testing regime, while our algorithm needs less than 15 minutes to find a good testing regime. And this budget of 34 reflects the reality of the budget that EPC had available in practice. And as I told you, the second goal of our study was to see how the people are affected from this protocol. So we had the treatment group where we're following the protocol that they could return back to in-person activities only if they had been it had been included in a negative test, versus the control group where they could just return back to in-person activities without any restriction. And so we measure how the performance and the mental health of the treated group had been affected versus the control group, and there was no evidence that there was a significant disadvantage of having the protocol. So due to lack of time, I'm not going to elaborate more on this. I'm happy to take more information offline about how we did that, how we modeled that. But I think the main takeaway is that we have a protocol by which people can safely return back to in-person activities, and their mental health and their performance and their productivity was not really affected. All right, and let me stop here. Thank you very much.
Great, we have time for questions.
Very interesting. Is there any relation or thought about like the test reliability?
No, we don't have included any. You mean what if it's false positive or false negative? No, we have not such results, but I think this is a very interesting direction to see. But in general, I feel that due to COVID-19, the ratio of false negative or false positive was quite low, so probably was not really affected our results, but yeah, that's an interesting question.
Did you do anything about incentives for people filling the survey for the utilities?
That's a good question. The truth is that we didn't have. However, some social scientists can disagree with that in the sense that we constructed the survey in a way that the answers appeared in uniformly at random, and some social scientists believe that because people are lazy to fill the different surveys, this is enough for not being strategic on how to choose which the different answers. We don't really agree with that, but yes, I think this is interesting how someone can construct a survey to retrieve the utilities without being obvious how people can manipulate the system.
Great talk. So, quick question. Have you thought about the trade-off between the informativeness of the test and the social welfare of the testees?
You mean when we don't know exactly the utilities and the...
Is there really like a trade-off between the test being informative about who is going to be negative, who is going to be positive, and also the expected welfare that you get?
What do you mean trade-off? I'm not sure.
Like, if I want to design a test that is more informative in some sense, is there any conflict between that and the social welfare objective, or do you think?
No, we don't have any other objective. It is about social welfare. Probably someone can consider different objectives, yeah, if that was the question.
Okay, thank you very much for that excellent presentation.